how the telecons are organized. There are a few core people who are very actively involved in the Einstein Toolkit development. I've encouraged a couple folks, in fact, with whom I spoke at this workshop, to please call in. Call in to the Einstein Toolkit telecons that are weekly. It can only help you. You can work on other things while something that you're not interested in is being discussed. But please, the more people we have involved in our day-to-day, our week-to-week discussions, the better I think we're going to be. And I'll hand the microphone to one of the lead developers, Rowan House.
So, I guess what I would say, if I look at what we'll need in the near future is, so a lot of the people here will have said, okay, we need our code to run these binary neutron stars, which is a challenging problem, it's really large. And for that, our code would need to run more quickly, run on more cores, maybe run some more different architectures, like the so-called GPUs and all of this. And I think if we want to have this in the Einstein Toolkit, we don't want to fall hopelessly behind the other frameworks that are out there, then we have to make a concerted effort. And it might be something where we have to say, okay, we actually have to say, if we want this done in a year, maybe, then we have to look at what other frameworks are out there, and we have to retarget the Einstein Toolkit framework. So we may have to be able to keep something that looks a little bit like Practice, but it may have a different underpinning, and it may behave different. So we will probably lose some of our cherished infrastructure points, and we'll have to re-implement them. I think that's the thing that we are facing, that we can't continue as we have so far. We need to change something radically to be able to compete science-wise in the future. That doesn't say that we should throw everything up. There's lots of good things in there. But I think we have to be willing to give something up, in particular in the higher codes.
So I think it was good that we started with Zach, because I think Zach is taking the Einstein Toolkit in some important new directions from NERPy. I'm hoping for great things from NERPy. I've always been a fan of Crank, but I've not been a fan of programming in Crank. Because Mathematica is, if you've ever tried to use Mathematica as a programming language, it's not a pleasant experience, at least for me. I mean, it's great if you're just doing calculations, but if you're actually trying to write a program, it's just a nightmare. Another thing I thought I would bring up in the area of sustainability, is one of the things that motivates people to contribute to a project is credit, right? And in any kind of project, usually the credit is, and the Einstein Toolkit so far is no exception, is you've got one paper that was written, sometime in the distant past with some set of authors, and that's the only thing that gets cited, and those are the only people that can get credit. I've been talking a lot with Dan Katz and other people who are interested in software sustainability. And they say that this is not a good model because it means nobody can join the project and get credit, right? So what they recommend for the future for everyone is that instead of having a paper that just lasts forever, you cite the software, you create a DOI with each release, and you cite that. And we're looking at moving to that model for Cactus. So if you're a student out there and you're thinking about a framework to join and you're hoping to someday get recognition for it, you might be able to have a DOI that says, yes, you're a developer for the Einstein Toolkit and you contributed to this release, and this release, I don't know, figured out the equation of state for neutron stars for all times. Maybe not that. Next.
In trying to think of the future, there is still one giant numerical relativity task out there that hasn't been mentioned as much yet, and that would be black hole neutron star merger stuff, for which the phase space and the amount of phenomena are equal, if not significantly larger in some ways, than either binary neutron star mergers or binary black hole mergers, because you've got both. There's still quite a future in numerical relativity, but I think the tenor of the discussions indicates, I think on the science side, if not the computer science side, but on the science side, if we now understand numerical relativity much better than we did a decade or 15 years ago now, to the point where, you know, we can attack problems and solve them or make rapid progress on them. The field of relativistic astrophysics is still kind of, you know, the wild west, the open country of all sorts of things going on. There are relativistic sources out there where we don't even really understand what the underlying model is supposed to be. You know, astrophysics is still the zoo of observed phenomenon, you know, some of which lack explanations at all. So it seems like, you know, as the numerical relativity community moves more in that astrophysics direction again, you know, there's broader classes of problems that many people here may not have even thought about yet. But you know, the opportunities are vast to attack many of these things, and it's going to be a matter of kind of selecting which projects can be attacked with existing codes or existing techniques, and then, you know, developing the ones that working out the low-hanging fruit and then kind of going after it. So yeah, I think we're still scratching the surface there.
Okay, since I moved back to Europe 6 years ago, I started to organize these Einstein Toolkit workshop schools in Europe, and the positive thing is that there has always been interest. So up to now, every year we were able to organize one in different countries in Europe, so that is very positive. So it means that the community is active and there's interest also outside the United States. Something negative instead is that every time we have these meetings, sometimes there are the same topics that come out every year. For example, we always discuss about the adaptive mesh refinement driver, the fact that we don't like carbon. I mean, carbon is very nice, but it's a bit limited. And so I know that we discussed, I don't know how many times, about importing some other drivers, like for example, I'm sure we mentioned Chombo, like we also discussing with, try to discuss with people like the developers of GR Chombo, this kind of stuff. And these kind of topics come out every year. And my question is, what is the situation from the point of view of the human resources on the programming side? Because it is my impression that we have a lot of people that have a very good understanding of the physics and the astrophysics, and so they're able to develop like GRMHD code and so on. But we are quite limited maybe on the side of the resources of people that really know how to code the core of Cactus and Carter, which is something that, for example, I cannot do because really I don't have the expertise.
Yeah, so I can come up with at least three options. One is we bring the Einstein Toolkit to the community through libraries by libraryizing it. I mean, there are many folks in this room who have their own code bases and maintain it and take care of them. It'd be great if the Einstein Toolkit were something more portable, where you could import it into your code. Another idea is we invite those of you who have your own code bases to add it to the toolkit and redefine the toolkit as just I think this is kind of how it's supposed to be defined anyway, as a broad brushed sort of consortium of different groups that focus in numerical relativity and relativistic astrophysics. And then just basically when you clone the Einstein Toolkit, instead of it being cloned in a directory called Cactus, I have a ticket out for this, by the way, it instead clones to something called the Einstein Toolkit, which is a broad, it's a broad set of different codes. And then the third option is something that Roland brought up, and sort of, I'll let him elucidate that idea. Add new drivers to the toolkit, right? We have the Hug-H driver, we have the Carpet driver, we can add a GR Chumbo driver, we can add a Spectre driver, what have you, and then figure out how to interoperate those with the rest of the token infrastructure moving forward. But that's not easy. But that's probably the hardest option. I don't know.
So, is there anyone in the audience who wants to comment first of all? Okay. So, now I'll make a bit of a statement. So, for adding a new driver. So, if we want to add a new driver, which I think is something we probably should consider, successor AMRX, they're very similar in outset from what Carpet is doing. So we're not getting anything that's fundamentally new. We're just tapping into the expertise that other funding agencies are putting in. AMRX is the one that DOE is funding, so they're putting in money there. This is the one that they want to use for the exascale systems. So there will be money in there. There's some people in the Einstein Toolkit that are a little bit involved in that. So, but adding this to practice will require a bit of work. So no one is really going to do this kind of in their free time and sit down because you don't have the time. However, what may possibly work is if there's maybe 3 or 4 people that are interested in this, we can get together, make a retreat for a week, and meet somewhere and sit down in that week. We should be able to get at least started hooking up such a driver. This is probably something where we can also get Eric involved in this, because he's the last person who actually hooked up a driver, Carpet, to the Einstein Toolkit, and then do so. And if we actually get together in a week, get maybe 4 people or so, maybe 5, that are interested in it, and then hook this up. Do a little bit of homework beforehand. There's a bit of an explanation how to do a mini driver, even in the practice documentation. And then it should be possible to get something up. It won't have the functionality of Carpet from the very beginning, but it might have enough functionality to solve just the PSSN equation to mesh refinement. There might not be checkpointing, there might not be interpolation, there might not be reductions, but you should be able to hook up fairly quickly just the hyperbolic pieces of the equation, which would be a good start, I would think.
I think this is a great idea. You want to comment? I
Oh,
think
yeah. There is another potential for a driver that I was looking at LSU. The HPX group, High Performance Parallels. It's this alternative to MPI. It's not quite as well developed as Charm++, but it's in that same vein. They have a code called Octatiger, which does white dwarf simulations. It's a Newtonian code, but basically it's a hyperbolic PDE solver. It could probably be adapted to become a Thorn, and there's some interest from that group to making that happen. Just sort of a random footnote from that. I seem to recall that they had a similar discussion about angular momentum conservation in that group. And they use Cartesian coordinates, but what they do is they convert the quantities to the spherical quantities at each point, do the differences, and then convert them back. I'm probably getting the details of that slightly off, but by doing something like that, they were able to conserve angular momentum with points that are on a Cartesian grid, is my understanding. I'm sure that the details are in their papers.
Okay. So there's more comment. If there's no comments, any comments from the audience about this?
If there's no comments, then I got a
Do
question.
you want to go first?
So one of several of the sticking points, especially for GPUs these days, that I remember from when they first got discussed, seem to have kind of largely fallen by the wayside. As I remember when people first started talking about numerical relativity with GPUs, the 2 main complaints were, 1, there was no double precision support, and 2, that CUDA was possibly more unfriendly than Mathematica at times to work with, or you know, was a difficulty. So the double precision support problem seems to have largely vanished. With tools like OpenACC, which is significantly more user-friendly, what is the time scale for that kind of hardware side adaptation of the tool at this point?
I should answer that. So I had an eager grant to explore this for the Einstein Toolkit, and we had this ambitious vision of you start with a description of a stencil and a PDE, and it gets generated, and from that you get code. The obvious advantage is you don't want to hard code your optimizations in your physics. You want to separate those. And I think that, and so we built a system like that, and it partially worked, right? The eager wasn't a lot of money. It wasn't enough to fund a production product, right? It was enough to just sort of do proof of concept kind of things. And we do have something that kind of works, right? You can create this kernel with this language that we developed, and you can generate highly optimized GPU code. Where it falls apart is once you try to use AMI, right? Because then suddenly you've got to do all kinds of prolongation and restriction, and all of that's done on the CPU, so you have to keep pulling things back and forth, and you lose all your performance. And then there was just the general problem that it wasn't production ready. But some of the, and I think maybe Python is a better way to go than Mathematica, which is what's underpinning it currently. But we've got some basic infrastructure in there for keeping track of grid functions and whether they live on a GPU or a CPU. And the read-write directives stuff is capable of being, we can use the read-write directive stuff to move the data back and forth from the GPU. So there is something there. We just said. It would take more money and more people to actually bring it to something usable, and I don't know where that will come from.
So I would like to, yeah, oh.
So I guess thinking about this and thinking about the difficulties in putting, let's say, an optimization, let's say GPU optimization in the toolkit, should we also just consider looking into infrastructures which have already basically solved this problem, and just consider moving our physics thorns into another infrastructure?
Yeah, and this is something, no, but this I think is a topic that we can continue in the next panel. And to summarize, I think there have been some ideas, some very cool ideas here. Obviously, from the audience, we have heard, and also from the Einstein Toolkit, we want to have more flexibility. All tools, NeuralP is great for code generation. We want that, more of that, to interface with the user community who wants to get engaged, to help us. But also the expert community doing simulation would like to be able to extract some of the key tools. Carpet, AMR drivers are the key recognized tools that we all want. Well, of course, apparent horizon finder, these things already exist. It's just a matter of packaging. But the AMR driver needs development. And then the great other idea that I heard is that perhaps the next thing we should be doing, in addition to this workshop, is to have smaller key developer meetings, frequent ones, where we allow them to meet and do the work that they need to do in order to get these things done. So I think that's something that we can take back home. And one of the things we should be doing is also add to our 7 notes of the future of the toolkit, what we discussed in this panel, and maybe ask the community to send feedback, additional feedback. Okay? And that would be helpful because it will allow us to move forward in the directions. It will set